Hello student to the Foundation of Classical Electrodynamics course. So, under module 3 today we have lecture 56 and today we will going to discuss about the magnetic dipole moment. So, we have today class number 56. So, let me quickly remind what we did in the last class, that we had a try to find out the contribution of. So, this is the coordinate system and we had a loop here, current carrying loop, and try to find out what is the vector potential A due to the current carrying loop, and we figure out that that was the structure. So, let us put it as x, y and z. This is at some distance r from the origin, and then actually we expanded. So, if I have a small section here, say dl prime, and where the dl prime, this is r prime. So, from here to here it was our curl r vector, which is r minus r prime. And when we figure out the value of A there at point r, it was the contribution of a monopole contribution, and then we have a contribution of dipole, and also the higher order terms are there. So, the monopole contribution. So, A, we started to with the expression of A with say mu 0 I divided by 4 pi using the line current, and then dl prime, and this is r minus r prime, and that was for closed line. So, there was a closed line integral, because this is a closed loop where we are having the amount of current I, and that 1 by this term actually we expanded. So, 1 divided by mod of r minus r prime, that term we expanded, and that is say n equal to 0 to infinity r prime to the power n divided by r n plus 1, and then we had the Legendre polynomials. So, we used it, we derived it during the multiple expansion problem in electrostatics. So, same thing here. Then the monopole contribution, if I write down the monopole contribution A monopole, that was mu 0 I divided by 4 pi, and then I had 1 by r closed integral dl prime, and that term was 0, because if you have a closed line integral over this vector L, it has to be vector dl, it has to be 0. So, what about the dipole contribution? Dipole contribution, the expression was mu 0 I divided by 4 pi, and then we had 1 divided by r square, and then this is r prime, and then cos theta d l prime vector. That was the expression, and then we mention that this term, actually this r cos theta. So if I consider this angle to be theta, then what we can get from here is this mu 0 I divided by 4 pi 1 divided by r square, and then I can write it as r vector, r prime vector dot unit vector r, and then d l prime. So, I just absorb this cos theta by putting the dot product between r prime and unit vector r, which one can explain from here, this figure. But after that we did one thing, and that is this quantity dot r we can write it as r cross integration d a prime, where this integration of d a prime was half of integration r cross dl. Last day we just used that and eventually figure out, okay, we used it what is written in blue line, and then finally we got the expression of the dipole, the vector potential due to the dipole contribution is something like mu 0 divided by 4 pi, and then a term called m, which is our magnetic dipole moment, and r square, where m was defined as current into area. Okay, that is called, this term is our magnetic dipole moment. Okay, but this thing we didn't prove actually, we just stated that. So, let us try to prove it. In Griffith's book, I guess there is a problem, and if you solve this problem, then eventually you prove that. So, let me try to do this. So, our goal here is to the proof that the closed line integral of unit vector r dot r prime and then dl prime, that is equal to minus of r cross dA or ds ds prime with s surface integral. So, that I need to prove, And let us start with the Stokes theorem. So, Stokes theorem is saying that the curl of a vector field A over the surface is simply the closed line integral of A over this. This is the Stokes theorem. Now, let us take this vector field A. This is any arbitrary vector field, is not A here does not mean that it is the vector potential. This is any arbitrary vector field. So, better I just put a different name to the confusion. So, let us put this as something, any vector field, say G, say G. So, G is here say some constant vector and a scalar field phi. C is a constant vector. The constant vector. Now, if I make curl of G, what we get? We get curl of C and then phi. That is simply phi and then curl of C minus C cross the gradient of phi. But this quantity should be 0 because C is constant. So, this will be 0. So, eventually we have this. So, now I can, so curl of G whatever is here I will put this side. So, in the Stokes theorem, so what we get is this minus integration C cross dot ds is C dot closed line integral then phi dl. So, I just put this curl cross G here in this equation and G is also C phi. So, C then I take outside. So, in this equation Stokes equation here I just put the value whatever I get. So, then after that we will going to exploit the expression like A vector dot B cross C is equal to B vector dot C cross A and that is equal to C vector, this is the vector identity A cross B. Exploiting this vector identity I can write as ds dot C cross this quantity is eventually C dot cross ds. Just playing with the vector identity to, and then I am going to put it here because in one term we have ds dot this C cross phi. So, this term I am going to replace this C dot. So, I have minus of C dot then integration of this quantity cross ds. Right hand side we already have c dot phi dl. So, you can see that this is true for any given c and phi. So, that means I can safely write that cross ds is equal to minus of integral of phi dl. So, this is one very interesting vector identity like Stokes law, like Gauss's integral theorem. Here we have a divergent, a gradient of a scalar field cross over a surface, that should be simply the integration of the scalar potential over this closed line. So, this is interesting, this is over surface and this is over closed line. So, this is interesting relation, vector relation that we figure out. Now, after that what we do, let phi, our scalar field, to be some vector, say t dot the position vector r. T is a constant vector and r is a position vector. So, t, this is a constant vector and r is our position vector. Okay. So, that thing, if I try to find out the, first I need to find out the gradient of these two quantity, and if I do, if I try to find out the gradient of t dot r, then we can, so this is the gradient of these two vector t and r, I can expand with the usual. So, this is not very simple, to be very honest. So, I just write the expansion. So, it should be r dot this over t, but mind you, t is constant, I am just writing the full expansion, then t dot this over r, then we have plus r cross this cross t, and then t cross r. That is the vector identity, but you can see that there should be many term that is 0. T is a constant and this will going to operate. So, this term is 0. C is a constant, it will operate. So, this term is also 0 and this term curl of r is also 0. So, this I have 0, this I have 0 and this I have 0. So, eventually this the term that we have here is simply t vector dot r. So, this is equal to this, okay, for constant t. So, then I can have, because I put this here, so gradient of phi. So, gradient of phi, now I put this gradient of t dot r, and gradient of t dot r is now t dot this quantity. So, I just put it here and I should have t vector dot the gradient the grad vector over r cross ds, that is the right hand side with a negative sign, I should have the integration and this quantity over dl. So, I should have t dot r and dl. Okay. So, here I am just writing this whatever the phi I am having, and that phi is here t dot r. So, I just write t dot r as a phi, this just exploiting this expression whatever we had. Now, let us check what is this quantity. So, t dot this over r is eventually, so here I should write simply T I delta I, that is operating on the vector r, and it simply gives me t vector, right. Please check it. So, it should be T x dx T y dy plus T z dz delta the operator z, partial derivative with respect to x, y and z, and then I am going to operate over the r vector. So, r vector in Cartesian coordinate system is simply x I plus y j plus z k. So, it simply gives me t. So, that thing gives me t cross. So, from here I can have this quantity is simply t vector, and t is a constant. So, I can write it as t vector cross ds is minus of integration t dot r dl. Okay. Now, we are there actually. So, if I just replace t to unit vector r and r to r prime vector, then I simply have our desired expression that we wanted to prove. So, let me write it here. So, then I simply have closed integral over line, then r dot r prime and then dl prime is equal to minus of r cross integral ds prime or dA prime. This is surface integral and this is closed line integral. So, this is essentially, so from here I just replace these two things, these two vector, and I finally figure out the desired result that we wanted to prove. So, this is a lengthy proof, but very tricky. So, you just have a look. This is just for once, you just need to check that you can understand these or not. But the thing that you need to remember is the expression of the this how the dipole the expression the magnetic vector potential for the dipole contribution is coming, and the dipole magnetic dipole is defined like current into area in this way. However, I can also have a alternative way to show it, but in terms of say vector potential the current density J, and that I quickly again there is some trick to prove certain identity, but I think I should show, at least I should mention this. So, we know, so this is the magnetic dipole moment, the expression of magnetic dipole moment, expression of magnetic dipole moment in terms of the current density J, which is normal in r prime, the function of r prime. So, how to do that? Because here the magnetic dipole moment M is defined, if I go back and check it, is defined here in terms of the line current, right, I, but I can have another expression where the magnetic dipole moment can be expressed in terms of the volume current density, because normally volume current density is something through which it is better to represent the magnetic dipole moment and others. So, let me do that. We know curl of B quickly is equal to mu 0 J, right. This is the source term, J is. Now, B is curl of A, and that gives me curl of A as mu 0 J. Now, curl of A, that is a very famous identity, and I can write that minus of grad square A vector plus divergence of A is equal to mu 0 J, right. Now, exploiting the Coulomb gauge, you can have this equal to 0, right, that we discussed last time. So, eventually the expression becomes a vector Poisson equation. This part also we did in the last class, is, say, let us put the plus sign. So, let us put this, and it is minus of mu 0 J, and the solution for this Poisson equation we wrote in this way. The solution is A, that is a function of r, and that value is mu 0 divided by 4 pi, and then integration of J r prime and dv prime divided by r minus r prime. Okay. So, please check it. When I expanded this today, the value of A, I wrote the value of A the very beginning. It was in line current, right, exploiting the expression of the line current, I started my calculation. But here the same expression I am writing in terms of the current density J. Now, if I expand 1 by r, so again I have a term 1 divided by r minus r prime here, right, and that is simply in 0 to infinity I have r prime whole to the power n divided by r n plus 1, and then I have p n cos theta. Now, these things if I expand, is 1 divided by r first term, second term is r prime divided by r square, and then cos theta, like before, the same thing. Now, I put these two here in this expression of A. So, I can write my A, which is a function of r, as mu 0 divided by 4 pi, the first term r, and then integral j r prime dv prime, and then I have the second term mu 0 divided by 4 pi then r square, and then I make an integral, and then I have j r prime dot r and then dv prime. So, here this is the contribution, also the higher order terms are there, because this is going on. We are, for the time being, we are not bothering about the higher order term. So, these things is equivalent to the monopole contribution, which is a function of r, and the next term is the contribution of dipole, and so on. Here two very important expression are there. So, I am not going to prove that but today, but if I have some time in some tutorial class, I will prove this as a tutorial problem. So, it can be shown that j r prime dv prime is 0, and that makes, this is a tricky proof. If you want to check this proof, the Sturm-Pollock, in the Sturm-Pollock book it is there, but if I have some time, as I mentioned, I will do that here in class. So, a, that makes a monopole term is 0, and the second identity that we are going to use is the integral of j r prime dot unit vector r dv prime. It can be written as a quantity like m cross unit vector r, where m, which is the dipole moment, now is defined in this way. This is now half integral of r prime cross j r prime and dv prime. So, magnetic dipole moment in terms of, so this basically gives me this expression, whatever the expression we are now having. So, I should have a vector sign here. So, whatever the expression now we are having is the magnetic dipole moment. This is the magnetic dipole moment term in terms of current density. J. Okay, in terms of current density, and A, from that I can write the A dipole contribution to be mu 0 divided by 4 pi r square, then m cross unit vector r. Okay, that is the dipole. So, you can now check that, you can now see that the magnetic dipole moment here is defined in terms of the current density. So, it is like electrostatics. If I go back to the electrostatic problem, in electrostatic problem what we had, the dipole moment P, the magnetic dipole moment P was charge into distance, that is the usual way we define, but also it is defined in terms of, it is also defined like r prime and rho r prime d v prime. This is the way we define in vectorial form, in integral form, exploiting the source term rho, right. Rho is the source term there. In the similar way for magnetostatic, the magnetic dipole moment M is defined like current into area in crude way, but also I can write it as some half into integral r prime cross j r prime dv prime. Here in electrostatic we have source term rho, that is why when you calculate divergence of E as a source, so rho by epsilon 0, this behave like a source, and curl of E was 0. Here we had on the other hand divergence of B is 0, but the source term is here, Ampere's law, mu 0 j. So, this source term I write here in dipole moment, electrostatic dipole moment, this source term I write here in expanding or in writing the dipole moment in magnetostatic. So, this is just to show the some sort of resemblance. Later we will see that how these magnetic dipole moments are there, but before going to finish, let us quickly calculate few the dipole moment for few cases. So, the first thing that we do is the magnetic dipole moment. This is simply current into area. So, okay, let me so this magnetic dipole moment quickly. So, M I had I integration of ds or dA, or simply I into area, current into area, that I write half I and area I can write it as half of closed integral r prime cross dl prime. So, that means if I have a loop here, current loop, this is a current loop and this is the direction of n. So, it is forming an area. So, if I have the section from here to here, small section, so this is dl prime and say this is my r prime. So, half of r prime cross dl prime, that is the area we are having, right, small area ds, and that is this shaded region. So, this is the area we are talking about. This is the area we are talking about. Now, if I make a total integration, simply over this closed loop where the current is flowing like this, then I should have closed loop integral r cross dl prime. That is the integration in the right hand side ds prime, and that gives me simply the total area with the direction. A is the area. So, M is simply current into area with, and this is the usual way we define. Now, what happened if I have a current loop not in a plane, but situated in this way. So, I have this coordinate system and the current loop is like this. So, let us go to the negative side as well. So, the current loop is something like from here to here, then here to here. It is folded, a book like, folded book like current loop, and the current that is passing through is say in this direction, here, 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 here. From here to here, say length is L, this length is also L, and here to here this length say L. So, we know the current, according to our usual notation, M is current into area, and here we have two area. So, let us divide by M, since we are having two areas. So, small m1 plus m2. So, small m1 is current into area if this length is L. So, this is L square and the direction should be along Z. Okay, let me put it as x, y and z. So, for this case it is z unit vector, and for m2 similarly we have I L square, unit vector will be along y. So, now if I want to calculate the total m, it should be simply the vector sum, that is all. So, it should be I L square and the vector sum of z unit vector and y unit vector. So, if I want to calculate the magnitude of m, it simply gives us root over of 2 and then I and L square. Okay, so that is quickly I try to calculate two different, just to show that how the magnetic dipole moment can be calculated in the when we have a loop which is not in the surface. So, next class what we do is we will go further and try to understand more about the practicality of this magnetic dipole moment, and then maybe we can move to magnetization problem, or before that we need to do the magnetic dipole moment in a external external magnetic field. If I put a magnetic loop in external magnetic field, how the torque will be there, etc. So, that maybe we can discuss. So, with that note I would like to conclude here. Thank you very much for your attention and see you in the next class.